Hey everyone, welcome back for another deep dive. Today we're taking a closer look at Chapter 6, Mechanical Properties of Metals. We'll be looking at what makes metals so strong and how engineers figure out how much stress they can take. It's really fascinating stuff, and you guys requested we deep dive on it, so here we are.
That's right. And it's really important stuff. This chapter lays the foundation. If you're designing anything from bridges to airplanes, you've got to understand how metals behave under pressure. We'll be talking a lot about stress, strain, and those tests that engineers use to figure out just how much a metal can handle.
Stress and strain, huh? Sounds a little familiar, like something we all experience in our daily lives, right?
Yeah, definitely relatable. Think about it this way. You stretch a rubber band, you're putting it under tension. That's a type of stress. Squash a marshmallow, and that's compression, another type of stress. And how much they change shape, that's the strain. How much the material deforms under pressure.
So it's not just about feeling it, it's about actually measuring it.
Precisely. And engineers use these measurements to predict how a metal will behave under load. That's why they have equations like 6.1 and 6.2. You wouldn't want to build a bridge without knowing exactly how much those steel beams can take before they buckle, right?
Okay, that's kind of a scary thought. So there's a science behind it, not just eyeballing it and hoping for the best.
Well, absolutely. And it's not just tension and compression either. There's shear stress, like spreading jam on toast. The force is parallel to the surface and it causes the jam to deform. Then there's torsion, like wringing out a wet towel.
Wow, so many ways to stress a metal out. But they do have their limits, don't they?
They sure do. It's like stretching a spring. At first, it springs right back. That's elastic deformation. But stretch it too far and it's permanently deformed. That's plastic deformation. The elastic limit is the point of no return.
So up to that point, it's like a rubber band. And beyond that, more like Play-Doh.
A perfect analogy. And up to that elastic limit, stress and strain have a beautifully proportional relationship. Hooke's law describes that. And the stiffness of a material, how much it resists deformation, that's measured by something called the modulus of elasticity, or E.
And this is where it gets cool for me. A higher E means a stiffer material. So tungsten, the metal used in those old-fashioned light bulbs, must have had a really high E to handle all that heat.
Exactly. Tungsten's high modulus of elasticity is what let it withstand those extreme temperatures. Think of it like this. The atoms are held together by bonds that act like tiny, super strong springs resisting deformation.
That's amazing. But what happens when we push a metal past its elastic limit into that Play-Doh zone?
Well, then we get yielding. The metal deforms permanently. The stress needed to start this permanent change is called yield strength, a crucial value for engineers. And then there's tensile strength, which is the ultimate stress a material can withstand before it breaks.
So yield strength tells us when it starts to give, and tensile strength is when it completely gives up. Makes sense. But I'm also wondering, some materials are more forgiving than others, right? Like some can stretch a lot before they break.
You're thinking of ductility. Imagine chewing gum. Some kinds stretch forever, others snap right away. Metals are similar. We measure ductility with percent elongation and reduction in area. Basically, how much can it stretch before it breaks? This is super important in manufacturing, knowing how much you can shape a metal before it cracks.
Okay, picture this. A rubber band versus a steel cable. Which one's tougher?
Ah, now you're getting into resilience and toughness. Resilience is the ability to absorb energy and bounce back like a spring. Toughness, on the other hand, is how much energy a material can absorb before it breaks. That steel cable, that's definitely tougher. It can handle a lot more punishment.
So the rubber band is more resilient, but the steel cable's the tough guy.
Yeah.
I like it.
Exactly. But here's a little twist. Sometimes the standard stress and strain measurements don't tell the whole story. Think about stretching a piece of taffy. It gets thinner as you pull.
Right.
So we have to account for that change in cross-section, and that's where true stress and strain come in.
Ah, so it's like adjusting for the fact that the metal is changing shape as we're testing it.
Exactly. And this is really important when we're talking about materials that undergo a lot of deformation. But what if you want to check a metal strength without, actually breaking it?
That's where hardness testing comes in.
You got it. Hardness testing is a quick and dirty way to assess a metal's strength. There are different methods, like Rockwell, Brunel, Knoop, and Vickers, each with their pros and cons depending on the material and the precision you need.
So it's like a quick checkup for the metal.
Exactly. But here's the thing. Even with the best manufacturing, no two pieces of metal are exactly alike. There's always going to be some variation in their properties.
Oh, that makes sense. Like, even if you bake a cake with the same recipe, they'll always turn out a little different.
That's a great analogy. And just like a baker adjusts their technique, engineers use statistics like average and standard deviation to understand the range of possibilities. They build in safety factors to account for those variations.
So we're not just aiming for good enough. We're aiming for super safe.
Exactly. Especially when we're talking about things like bridges and airplanes. Building in that extra margin of error is crucial.
This is also fascinating. We've covered so much. Stress, strain, elastic limits, yield strength, tensile strength, ductility, resilience, toughness, true stress, hardness testing, and even the fact that no two pieces of metal are exactly alike.
You've been a great listener. And we've only just scratched the surface. There's so much more to explore when it comes to metal strength.
Well, you've definitely got me hooked.
Great. Let's move on to the next chapter of our metal adventure. Now let's imagine you're designing something like a car axle or a bridge beam, something that's going to be loaded and unloaded over and over again. That's when you have to think about fatigue.
Fatigue. Like when I'm tired after a long day. Do metals get tired too?
Well, it's not exactly the same thing, but the analogy kind of works. Metal fatigue is when a material fails, even if the stress is below its yield strength, just because it's been subjected to that stress repeatedly over time. Like if you bend a paperclip back and forth, eventually it'll snap.
Oh, I've done that plenty of times.
Yeah.
So it's like with each bend, the metal gets a little weaker until it just can't take it anymore.
Exactly. Microscopic cracks can form and grow over time, and eventually it leads to a big failure. It's something that engineers have to be really careful about, especially in things like airplanes and bridges, where safety is super important.
So how do they deal with metal fatigue? Do they just use stronger materials?
Stronger materials definitely help, but that's not the only solution. One thing engineers do is design things with smooth, rounded shapes to avoid those sharp corners and notches where cracks like to start.
Oh, so it's like streamlining a car to reduce wind resistance.
Exactly. And another thing is surface finish. A polished surface can have fewer spots for cracks to start. And of course, choosing the right material is crucial. Some metals are naturally more resistant to fatigue than others.
This all makes sense, but I'm curious how engineers actually predict fatigue life. Do they really just bend paper clips back and forth until they break?
Haha, no, there are more sophisticated methods than that. They have special fatigue tests where they put materials through controlled cycles of stress. And by analyzing the results, they can create models that predict how long a component will last under specific conditions.
So like a stress test, but for metals.
You got it. And these tests are super important for making sure that everything from airplanes to bridges to even medical implants are safe and reliable.
Wow, it's amazing to think about everything that goes into designing something as simple as a paperclip, let alone a bridge or an airplane. It seems like understanding material properties is really just the beginning.
It really is. Material science is a huge and fascinating field. And yeah, we've only just scratched the surface here, but hopefully you're starting to see just how complex and how important this stuff is. But now, let's talk about something else. How do you actually make a metal stronger? We've talked a lot about how we measure strength, but what about improving it?
Okay, yeah, that's what I want to know. Can you actually make a metal stronger than it already is?
Absolutely. There are a bunch of techniques that metallurgists and material scientists use to beef up a metal's strength. One of the most common ones is alloying. That means adding other elements to a base metal to change its microstructure and improve its properties.
So it's like adding spices to a dish to make it taste better.
Haha, I like that analogy. For example, if you add carbon to iron, you get steel, which is way stronger and more versatile than plain old iron.
Ah, so steel is like iron with a superpower. Are there other ways to make metals stronger?
Yeah, definitely. There's work hardening, which is also called cold working. That means you deform the metal at room temperature. This creates little imperfections in the crystal structure, which actually make it harder and stronger.
Wait, so you can make a metal stronger by messing it up a bit?
In a controlled way, of course. Think about bending that paperclip again. It gets harder and more brittle where you bent it.
Okay, I'm seeing a pattern here. We can manipulate the internal structure of metals to change how they behave. What other tricks are there?
Well, there's heat treatment, which uses controlled heating and cooling cycles to change the metal's grain structure. This can make it even stronger and tougher.
It's like you're giving the metal a spa treatment, but with heat and deformation instead of cucumbers and face masks.
Yeah, that's one way to put it. And these are just a few examples. Material science is always advancing, and researchers are always coming up with new ways to tweak the properties of metals for different applications.
It's amazing, all this hidden complexity. But what happens when things go wrong? I mean, we've talked about all these ways to measure and improve strength, but what about when metals fail unexpectedly?
That's a great question, and it brings us to the idea of failure analysis. When a component fails, engineers need to figure out why. Was it a bad design? A problem in manufacturing? Was the material just overloaded?
So it's like detective work, but for metals.
Exactly. They'll look at the fractured surfaces, analyze the microstructure, consider the history of how it was loaded, all to figure out the root cause, and then they use that information to prevent similar failures in the future.
That sounds like a really important process, especially for things like airplanes and bridges.
Absolutely. Failure analysis is crucial for keeping those critical structures safe and reliable. It's a constant learning process as engineers try to understand the limits of materials and design things that can withstand the challenges of the real world. Now, let's dive into something even more interesting: the connection between the microstructure of a metal and its mechanical properties.
Microstructure. Are we talking about things so small I need a microscope to see them?
You got it. Microstructure refers to how the grains, phases, and other tiny features are arranged within the metal. It's like looking at the fabric of the metal up close.
Okay, so if the macrostructure is the big picture, the microstructure is the zoomed-in view. But why is it so important?
Because it turns out that the microstructure has a huge impact on the mechanical properties of a metal. For example, the size and shape of the grains can affect its strength, ductility, and toughness.
So it's not just about what kind of metal it is, but also about how its internal building blocks are arranged.
Exactly. By controlling the microstructure, metallurgists can actually tailor the properties of metals to meet specific needs. A fine-grained microstructure usually means higher strength, while a coarse-grained one might mean higher ductility.
It's incredible to think that something so small can have such a big impact on how a metal behaves.
That's the beauty of material science. There's a whole hidden world beneath the surface, and the more we understand it, the better we can design and create amazing things.
This deep dive has really been eye-opening. I'm starting to see metal strength in a whole new light. It feels like we're just getting started, though.
You're right, there's still a lot more to explore in the world of metals, from the amazing processes of phase transformations to the cutting-edge techniques for developing new alloys.
Well, I'm ready for more. What else do you have for us?
Let's jump into the world of phase transformations.
Phase transformations. Sounds kind of sci-fi, like something out of Star Trek.
Haha. Not quite teleporting matter, but it is pretty cool. Metals can actually exist in different phases, kind of like how water can be ice, liquid water, or steam. And these transformations, they can really change the properties of a metal.
So we're not just talking about melting and solidifying. There's more to it.
Oh yeah, way more. For example, steel. Remember, we've talked about that. Steel goes through a really interesting transformation when you heat it up and then cool it down. By controlling those heating and cooling rates, you can actually rearrange the iron and carbon atoms inside the steel and create different microstructures, each with its own set of properties.
So it's like we're playing Tetris with atoms, rearranging them to get the properties we want.
That's a great way to think about it. And these phase transformations, they're the basis for a lot of the heat treatment processes that we use to make metals stronger and tougher.
It's blowing my mind. I never realized so much was going on at the microscopic level that could affect how a metal behaves.
It's a whole hidden world down there, and it gets even more exciting when we start talking about advanced alloys.
Advanced alloys. What makes them so advanced?
Think of them like the superheroes of metals. These are alloys that are designed to handle really extreme environments or crazy demanding conditions. They might be super strong or lightweight or resistant to corrosion or able to withstand really high temperatures.
So these are the metals they use in, like, spaceships and jet engines and nuclear reactors.
Exactly. For example, superalloys. They're a type of advanced alloy that's used in gas turbine engines where they have to withstand temperatures that are close to their melting point, all while being under incredible stress.
That's wild. How do they even create metals that can handle that kind of punishment?
It's a combination of things. You need the right alloying elements, really sophisticated processing techniques, and precise heat treatments. It's like all of material science working together to create a material with extraordinary properties.
Wow. This has been such an incredible journey into the world of metal strength. I feel like I've learned so much, but I also know there's still so much more to discover.
You're absolutely right. Material science is a huge and constantly evolving field. But hopefully this deep dive has given you a good foundation and made you curious to learn more.
Definitely. It's amazing to think about all the incredible things we can create when we understand how to harness the strength of metals.
Absolutely. The world of materials is full of possibilities, just waiting to be discovered and used to build a better future.
I love that. And for our listeners who are as fascinated by this as we are, be sure to check out the resources we've mentioned, and don't hesitate to reach out if you have any questions.
We love talking about material science, so feel free to contact us. Now, as we wrap up, let's think about this. The strength of a material isn't just about its inherent properties, it's also about how well we understand those properties and how we use that knowledge to meet our needs.
That's a really great point. It's like we have the power to shape the world around us, quite literally, by understanding the materials that make it up.
Exactly. So, as you continue exploring material science, remember that you're not just learning about metals, you're learning about the building blocks of innovation and progress.
What an inspiring thought. Thanks for joining us on this deep dive into the fascinating world of metal strength. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible.
And remember, the strength of a material isn't just about its physical properties, it's also about the ingenuity and responsibility of the people who design and build with it.
Well said. Thanks again for joining us on the deep dive. We'll catch you next time for another exciting exploration of the world around us.